Hey everybody, it's John again. In this video, we're going to go through a couple of different things, but I want to start with solving for x. We're going to get a lot more into solving exponential equations next week, but I want to sort of plant a little bit of a seed here so that we're ready to solve some of these problems that don't require logarithms that we could do just taking advantage of our exponent rules. So what I have here is I have 5 raised to some exponent is equal to 1 over 25. I'm looking to solve for x, but I can take advantage of the fact that I can rewrite 1 over 25 as 5 to some power. So 1 over 25 can actually be written as 5 to the negative 2. And if you stop and think about that for a second, you might not have thought to do that, but now that I'm telling you, hopefully you can look at that and say, oh yeah, 1 over 25 is 5 to the negative 2. The negative exponent makes it 1 over 5 squared, and 1 over 5 squared is 1 over 5 times 1 over 5, which is 1 over 25. Now, why would I want to rewrite it so that the base is 5 as well? Well, because now this is an equation. This symbol right here means that both sides of this equation aren't even different things. The equal sign means that they are the same. It's not just that they're equal, but they are not any different from one another. So if we have 5 raised to some power is equal to 5 to the negative 2, that means that the sum power has to be equal to negative 2. So I can get rid of the bases altogether and just say, hey, this exponent has to equal negative 2, because if these are not even different things, 5 raised to something that I don't know being the same as 5 raised to the negative 2 means the something I don't know has to be negative 2. So I'm just going to distribute the x here. It's going to give me x squared minus 3x. And I'm going to add 2 to both sides so that I can get this in quadratic form. And now this looks like something I might be able to factor, because factoring is my favorite way to solve a polynomial. So we have x times x gives me x squared, and then negative 2 and negative 1 multiply to give me positive 2 and add to give me negative 3. And so x equals 2, x equals 1. And we just want to make sure that both of these work in the original equation. So 5 raised to the second times 2 minus 3. Is that equal to 1 over 25? Let's find out. So 2 minus 3 is negative 1 times 2 is negative 2, which is definitely 1 over 25. And when we plug in 1, one minus 3 is negative 2, so 1 times negative 2 is also negative 2, and that indeed equals 1 over 25. So both of these work. We solved for x. We won. Okay, so you're going to see some problems like this on the problem set, and I want you to be mindful that you're going to have to look at the base of the other side and see if you can get the two bases to be the same so that you can take advantage of equality and just set the exponents equal to one another. All right, we're going to change directions very quickly here and talk about transformations. Okay, so the transformations that we did in the previous unit, they're not going away. They're going to be used because they can be used for any function. And since exponentials are functions, we can say if we're adding inside, that's going to move things to the left. If we're subtracting inside, that's going to move things to the right. If we're adding or subtracting outside, it's going to move things up or down. If we multiply on the inside, it's going to horizontally stretch and compress. If we multiply on the outside, it's going to vertically stretch and compress. And if we put negative signs on the inside or the outside, it's going to reflect both in the y and x directions, respectively. And so what do I mean by inside and outside when we're talking about an exponential? Well, inside the function is going to be the exponent. Okay, so if something's happening in the exponent like x minus 3, this is subtracting 3 inside the function. And so this is going to shift my function 3 to the right. Whereas if I subtract 3 here, this is not in the exponent, so this is outside the function. And this is going to move my function 3 down. Okay? If I multiply by a negative on the inside, meaning in the exponent, that's going to reflect over the y-axis. Okay? And that actually makes sense because this negative exponent takes the reciprocal of the base. And so if this base was bigger than 1, it would have been growth, but because of the negative exponent, it's now decay. And if you think about how growth reflects over the y-axis to become decay, or some vertical line, that kind of should make sense in your head. If we have a negative out here, it's actually going to, if you have something like growth ahead of time, it's going to reflect over the x-axis. So now this is still considered growth, but it's growing negatively, so it's getting more negative as you go. So those are all the transformations that could happen. So let's just quickly go through some of these transformations. As I said at the beginning of this lecture, the domain for all of these is going to be all real numbers all the time. Okay? So we can get that out of the way right now. The domain for all of these is all real numbers. You don't need to know anything about it other than it's an exponential function, and that tells you that the domain is all real numbers. Now the range, remember when we first graphed one of these, we talked about there being a horizontal asymptote along the x-axis. Now the only way that's going to change if I'm growth or even if I'm decay, okay, the only way that this horizontal line y equals 0 is going to change is if I have a vertical shift up or down. So on this first one, that line is going to get shifted down. So here, there's no shift. So the range is going to be y equals, well, the horizontal asymptote is going to be y equals 0. So the range is going to start, let's do this one instead. The range is going to start at 0, but not including 0, and go all the way to infinity. The problem with g of x here is because of this negative in front, that horizontal asymptote is still at y equals 0, except now this is it's reflected over the x-axis. So it's actually all negative values. So for that one, we're going to start at negative infinity and end at 0. This one here is just shifted down 4. So my axis, my horizontal asymptote has been shifted down 4, but it's still growth. So it's going to start at negative 4 and go all the way to infinity. And this one here has been shifted up 2. It would have been growth, but it's reflected over in the x-axis, so it's actually growth negative. Okay, but it's now reflected over this horizontal asymptote, which is y equals 2. So we're still at 2, but we're starting at negative infinity going up until 2. So if you see this negative out in front, you're going to start at negative infinity for your range and end at the horizontal asymptote. Okay? So now that we've got the range, I've actually pretty much graphed these already. And I don't need anything more accurate than that. And Pearson's not going to ask you any more than to pick from a graph. I don't think it's going to actually ask you to graph them by hand. And if it does, I don't think it's going to ask for more than 1 point. All I'm looking for, all I want to see is that the point that used to be 0, 1 when I plug 0 in, okay, where has that moved? For this one, it's moved 1 to the left. So it would be negative 1, 1. Okay, so plot that point. It's growth. Okay, you know that y equals 0 is the horizontal asymptote. We have growth because 3 is bigger than 1. And so what I'm going to see on my graph is that at negative 1, 1, you have a point plotted. You have your horizontal asymptote at y equals 0. And we're dealing with growth. Okay? So that's the only information I really care about. So on the problem set, it's just going to ask you to pick from a couple of graphs. I don't even know that I asked you to graph, actually. Because I don't think graphing exponentials is that important. I think it's more important to deal with the exponent rules and to understand what this means, and to use these for application, because there's so many applications for exponential functions. Okay, so I'm not going to go through and graph every single one of these. This one I kind of already did. This one was shifted down 4, and it looks like this. So this would be 0, negative 3, because it was 0, 1. It got shifted down 4, which brings me down to negative 3. It's growth, and this is y equals negative 4. This right here, this graph right here is g of x. It would have been just growth going through 0, 1, but it was reflected over the x-axis. So now this is 0, negative 1, and it's still growing. It's just growing negatively. It's the reflection of a growth. I just plotted h of x down here, and then f of x, big F of x, is this graph right here, where this point, so this point here would have been 0, 3, because it was shifted up 2, but then it was reflected over, so this is actually back to 0, 1 again. And its growth down, where this is y equals 2 is the horizontal asymptote. Okay, I hope that all makes sense. If it doesn't, you can rewatch this. But again, I'm not that concerned about very accurate graphs of exponentials. I'm more concerned about the application, okay, which we'll talk about in the next video.